In section 5.2, we will talk about power functions and a polynomial function. First, let's take a look at the definition of a polynomial function. A polynomial function of degree n, where n is a non-negative integer. So non-negative integers are 0, 1, 2, 3, etc., etc. It's given by a sub n x to the n plus a n minus 1 x to the n minus 1, etc., etc. And notice that the degrees are written from highest to lowest degrees. The leading term, a sub n x to the n, so the first term here, this is called the leading term, and the a sub n, this is called the leading coefficient. Okay, so this is important to know. A sub n, this is called the leading coefficient. The a sub 0 is called the constant term. It doesn't have a variable attached to it, so this is going to be the constant term. The degree of the polynomial is the largest power of x that appears. A polynomial function is in standard form if the polynomial that defines a function is written in descending order from highest to lowest degree. So standard form always means the degree is written from the highest degree to the lowest degree. And we always write polynomials in standard form. So for example, f of x equals to 2, this is a constant function because we have no variables. The degree is 0, and the leading coefficient is just 2. We can also write 2 as 2 times x to the 0 power, which is why the degree is going to be 0. 5x minus 1, this is called a linear function. We know that if we graph this, we get a line. The degree is 1 because the highest degree of an x is a 1, and the leading coefficient is a 5. For 4x squared minus x plus 1, this is called a quadratic. Anytime we have the highest degree of power of 2, that's a quadratic function. Which we talked about in the previous section, has a degree of 2, leading coefficient of 4. 2x cubed minus 1 half x plus 5 is a cubic function with a degree of 3 and the leading coefficient of 2. So degree is the highest power of x, and the leading coefficient is a coefficient for the leading term. X to the fourth plus radical 2x cubed minus 3x squared, that's called the quartic function with a degree of 4, and the coefficient of the x to the fourth is a 1, so the leading coefficient is going to be 1. So those are just some basic definitions. Now, a power function is a monomial function. Monomial means one term, of the form f of x equals ax to the n power, where a is a real number and n is an integer. Okay? The end behavior, so here's what the end behavior means. The end behavior, it means that as the function keeps going infinitely in each direction to positive and negative infinity, what's happening to the function? Is it going towards positive infinity? Is it going towards negative infinity? What's happening? So the end behavior of the polynomial graph is determined by the leading term. That is a term of the greatest degree. The end behavior of a graph, the end behavior is the behavior as x approaches positive infinity and as x approaches negative infinity. And we'll see this more in examples. But basically, end behavior refers to as x's get infinitely large and as x's get infinitely small, what happens to the graph. Okay, so a polynomial function f of x is in this form. And here's the cool thing. Any polynomial function is going to resemble the graph of the power function, which is a sub n x to the n. So all we really have to worry about is the leading term. And the leading term is going to tell us about the end behavior of the graph. So for example, the function 5x cubed minus 3x squared plus 5x plus 8 has the exact same end behavior as 5x cubed. And we will see this during class. I'll show you guys these graphed, and I'll show you what that means, what I'm talking about during class. But feel free to graph these both on Desmos as well to see the end behavior on your own. All right, now here's the end behavior of polynomial functions. So I'm going to break this up for you into 4 different cases. The first case is an even degree. An even degree is something like x squared or x to the fourth or x to the sixth. And a greater than 0, it means that their coefficient is going to be positive. So the number in front of the even degree of the variable is going to be positive. In that case, the graph might look a little bit different in the middle, but the end behavior is going to be the same. As x approaches infinity, the graph approaches positive infinity, and as x approaches negative infinity, the graph approaches positive infinity. And the easiest way I think to remember this is to look at the graph of y equals to x squared. So this is an even degree, and the coefficient, the leading coefficient, is greater than 1 or greater than 0, so it's positive. And that graph is going to look like this. So it's going to approach positive infinity as x approaches infinity and negative infinity. Now, what if we have an even degree? So, we have something like an x squared or x to the fourth, but the leading coefficient is negative. In that case, the graph is going to approach negative infinity. And once again, the easiest way to think about this is think of the graph of y equals negative x squared, which is going to approach negative infinity on both sides. So here, as x approaches infinity, f of x, or the graph, approaches infinity also. And as x approaches negative infinity, the graph also approaches infinity. However, if the a value, or the leading coefficient, is negative, then as x approaches infinity, the graph is going to approach negative infinity. So as x gets bigger and bigger and bigger, the graph is going to approach negative infinity. And as the x gets smaller and smaller and smaller, the graph also is going to approach negative infinity. So anytime you think of an even function, think of the graph of x squared or negative x squared. X squared if it's a positive leading coefficient, negative x squared if it's a negative leading coefficient. Okay, let's think about the graph of y equals to x cubed. So in this case, the degree is an odd degree, which means the exponent is an odd number, and the leading coefficient is greater, I'm sorry, this should be greater than 0. Shouldn't say 1, I apologize. So, obviously 1 or higher. So here, a greater than 0, so that shape is going to look like this, where as x gets bigger and bigger, the graph is going to approach infinity, and as x gets smaller and smaller, the graph is going to approach negative infinity. And notice the difference between an even and an odd function. In an even function, both directions they approach the same side. They either both approach positive infinity or they both approach negative infinity. But on an odd function, one side approaches positive infinity and the other side approaches negative infinity. Let's say we have an odd degree. So we have, an odd degree is like x to the third, x to the fifth, x to the seventh, etc., etc., but the coefficient is negative. In that case, as x approaches negative infinity, so as x gets smaller and smaller, the graph gets bigger and bigger. So as x approaches negative infinity, the graph approaches infinity. And as x approaches positive infinity, the graph gets smaller and smaller and is going to approach a negative infinity. Okay? So just memorize these 4 graphs, and that's going to apply for any even or any odd degree. Okay, so here's an example. Find the end behavior of the following polynomials. So the first one, we have f of x equals to negative x to the 6 plus 5x cubed minus 1. And all I'm looking at is the leading coefficient. That's all I care about. My leading coefficient is negative x to the 6th. Now, I'm going to ask myself 2 questions. Is it even or odd? So this one is an even degree. And is my leading coefficient positive or negative? So this time my leading coefficient is negative. So I think of which of these graphs, so remember, these are the only 4 graphs you have to memorize. Which of these 4 graphs have an even degree and a leading coefficient that's negative? It's going to be this graph right there. So I know that this graph, negative x to the 6 plus 5x cubed minus 1, is going to have end behavior that resembles this shape. So as x approaches infinity, as x's get bigger and bigger, f of x, or the graph, approaches negative infinity, and same thing, as x approaches negative infinity, it gets smaller and smaller, f of x also approaches negative infinity. Okay, in part B, we got f of x equals to 2x to the 5th. So I'm going to ask myself 2 questions. Is the graph even or odd? In this case, the graph is odd. Is my leading coefficient positive or negative? In this case, my leading coefficient is positive. So which graph does that resemble? It resembles the y equals x cubed graph. Okay, so think of the shape of this graph. The shape of this graph is going to look something like this. So as x's get bigger and bigger, the graph is going to approach infinity. As x gets smaller and smaller, the graph is going to approach negative infinity. In even functions, the graph approaches the same value, negative or positive infinity. And for odd functions, one side approaches positive infinity, the other one approaches negative infinity. Okay, let's take a look at the next one. We got f of x equals to 5x cubed plus 3x minus 2x to the 7th plus 1. This is kind of a trick question. It makes it seem like the leading coefficient is 5x cubed, but the leading coefficient is the one that's the coefficient of the highest degree, or the leading term. So I'm going to rewrite this as f of x equals to negative 2x to the 7th plus 5x cubed plus 3x plus 1. Now I can see that this is an odd function with a negative leading coefficient. So that's going to resemble the graph of y equals negative x cubed, which is going to look something like this. So as x approaches negative infinity, the graph approaches positive infinity. And as x approaches positive infinity, the graph approaches negative infinity. Lastly, I'm going to once again rearrange this from highest to lowest. So we have 3x to the 8th plus 5x to the 4th minus 7x squared plus 4. So here we have an even degree with a positive leading coefficient, which means it's going to look like this. So as x approaches infinity and negative infinity, the graph is going to approach positive infinity. All right. Let's talk about turning points. The turning point, a turning point is a point at which the graph changes directions, which means it goes from being increasing to decreasing or from decreasing to increasing. So it looks like this. It goes from being increasing to decreasing, or it goes from being decreasing to increasing. So these points are called turning points. Now, here is what we need to know about turning points. If f is a polynomial function with a degree n, then it has at most n minus 1 turning points. So that kind of is weird, like it's backwards. So basically, if f has n minus 1 turning points, the degree of f is at least n. So the degree is always equal to, or the least degree is always equal to the number of turning points plus 1. The least possible degree of a polynomial is the number of turning points plus 1. So in this case, what is the least possible degree of the polynomial graph? So I'm going to ask myself, how many turning points, what is the number of turning points? So in this case, I only have one turning point. So the least possible degree, is going to be n plus 1, which is 1 plus 1, or 2. Which kind of makes sense, right? This is the shape of a quadratic, so it has a degree 2. But the reason it says least possible degree is because like x to the 4th, x to the 6th, that those will all have the same basic shape. But the least possible degree is going to be 2. Here's another example. What is the least possible degree of the polynomial graphed above? So let's count the number of turning points. The graph turns here, that's 1 turning point. The graph turns here, that's 2 turning points. The graph turns here, that's 3 turning points. And the graph turns here, that's 4 turning points. So the number of turning points equals to 4. And so the least possible degree is going to be n plus 1, which is 4 plus 1, or 5. So the lowest degree you can have is going to be an x to the 5th polynomial. Okay, that's it for this section.